Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should make your brain happily ache with wonder. Imagine holding a single sugar cube in the palm of your hand. It's light, perhaps a gram or two, easily crushed between your fingers. Now take that exact same volume, a tiny sugar cube, and imagine it weighing not a gram, but 1 billion tons. That's a B for billion. 1 billion tons. To put that into perspective, a single billion tons is roughly the combined weight of every single car, truck, bus and motorcycle on Earth, multiplied by 100. Or, if you prefer, is about the weight of every single human being on Earth, stacked together about 25 times over. All of that mass compressed into a space no bigger than a sugar cube. It's a concept so wildly beyond our everyday experience that it almost feels like a trick, a mathematical impossibility, or a fever dream. And yet, this isn't science fiction. This isn't a theoretical limit that we might one day reach. This is an actual physical reality found in the universe, an everyday occurrence in the cosmic sense. We're talking about the density of a neutron star. These objects are not just dense, they redefine what density even means. They are the ultimate cosmic crush, the universe's most extreme experiment in packing matter together, second only to the singularity of a black hole. And what makes them endlessly fascinating isn't just their unbelievable weight, but how they get that way, what they're made of, and the profound implications of matter pushed to such unimaginable limits. Understanding neutron stars isn't just learning about a distant astronomical object, it's an exploration of the fundamental forces that govern everything, from the smallest subatomic particles to the largest galaxies. It's about seeing gravity in its most brutal, uncompromising form and witnessing matter's desperate struggle against it. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with a thought experiment that genuinely breaks our intuition. Imagine taking Mount Everest, the tallest peak on Earth, a colossal mass of rock and ice, weighing an estimated 60 trillion pounds. Now shrink it down until it fits into a space no larger than a grain of rice. That's the kind of mind-bending compression we're talking about when we discuss the density of a neutron star. A single teaspoon of neutron star material would, in fact, weigh about 1 billion tons. This isn't just a big number. It represents a state of matter so extreme, so fundamentally different from anything we encounter in our daily lives, that it forces us to rethink what matter itself truly is. To truly appreciate this, we need to begin with a clear understanding of density. At its core, density is simply a measure of how much stuff is packed into a given amount of space. Scientifically, it's defined as mass per unit volume. We experience density all the time, even if we don't consciously think about it. For instance, if you pick up a block of wood and then a block of iron of the exact same size, the iron feels much heavier. That's because iron is denser than wood. Its atoms, while still mostly empty space, are packed more closely together, and the individual iron atoms themselves are more massive than the carbon, hydrogen and oxygen atoms that make up wood. Water has a density of about 1 gram per cubic centimetre. A common rock might be 2 or 3 grams per cubic centimetre. Iron is about 7.8 grams per cubic centimetre. Lead, a very dense metal, comes in at 11.3 grams per cubic centimetre. These are all things we can easily conceptualize and experience. But here's the thing that often goes unsaid. Most of the stuff we interact with, whether it's a solid, liquid or gas, is overwhelmingly empty space. Yes, that's right. If you were to zoom in on an atom, you'd find a tiny, incredibly dense nucleus at its centre, surrounded by a vast, comparatively empty expanse where electrons zip around. If an atom was scaled up to the size of a sports stadium, the nucleus would be no bigger than a pea in the centre of the field, and the electrons would be like tiny dust motes buzzing around in the furthest reaches of the stadium. The solidity of a table or the hardness of a diamond isn't because the atoms are physically touching each other. It's because the negatively charged electron clouds of adjacent atoms strongly repel each other, creating an electromagnetic force that prevents them from interpenetrating. It's like trying to push two strong magnets together at their repulsive poles. They never truly touch, but they exert a powerful force that makes them feel solid. So if normal matter is mostly empty space, how do you get something as incredibly dense as a neutron star? The answer lies in the most fundamental force of the universe, gravity. When a star much more massive than our Sun reaches the end of its life, it runs out of nuclear fuel. During its long life, the star maintains a delicate balance. The outward pressure from the intense heat and radiation generated by nuclear fusion in its core pushes against the inward pull of its own immense gravity. It's a cosmic tug of war. But when the fuel runs out, fusion stops and the outward pressure vanishes. There's nothing left to resist the crushing weight of the star's own mass. Gravity, now unchecked, begins to win, and it wins spectacularly. For a star with a mass roughly 8 to 20 times that of our Sun, this collapse is catastrophic. The star's core implodes at incredible speeds, reaching about a quarter of the speed of light. The outer layers of the star rebound off this super-dense core in a spectacular explosion we call a supernova, briefly outshining entire galaxies. But it's the core that's truly fascinating. As it collapses, gravity crushes atoms with such force that the electron clouds, which usually provide that electromagnetic repulsion, are utterly overwhelmed. The electrons are no longer able to orbit freely. They are squeezed into the atomic nuclei where they combine with protons to form neutrons. This process, called inverse beta decay, essentially transforms an entire star's core into a giant atomic nucleus. The protons and the electrons cease to exist as distinct particles within the traditional atomic structure. All that's left is a sphere composed almost entirely of neutrons, packed together with no empty space between them. Imagine squeezing all the air out of a sponge and then continuing to squeeze the sponge itself until its very atoms were crushed. That's a crude analogy for what happens. The electrons, which normally provide the outward pressure in a white dwarf star, a less massive stellar remnant, are forced to merge with protons. This eliminates the vast emptiness that defines normal atoms and allows matter to be packed to an extreme degree. This is why a teaspoon of neutron star material weighs 1 billion tons. It's not just dense, it's matter stripped down to its most fundamental components, with virtually all the empty space removed. The density is so extreme that if you were to drop a bowling ball onto a neutron star, it wouldn't even make a dent. The bowling ball would simply merge with the neutron star's surface, its atoms utterly destroyed and integrated into the super-dense neutron fluid. This incredible density has profound implications. The gravitational field at the surface of a neutron star is quadrillions of times stronger than Earth's. If you were somehow able to stand on its surface, you wouldn't, of course, you'd be instantly crushed. A feather dropped from a height of just 1 meter would hit the surface with the energy of thousands of nuclear bombs. The escape velocity, the speed you'd need to travel to escape its gravity, is about half the speed of light. This means that even light itself struggles to leave a neutron star, getting significantly bent and warped by the intense gravity, a phenomenon predicted by Einstein's theory of general relativity. So, we've begun our journey by grappling with the almost inconceivable density of these cosmic behemoths. We've seen how the relentless power of gravity, when unleashed on a dying massive star, can fundamentally alter the very fabric of matter, collapsing atoms into a uniform sea of neutrons. But what exactly is this neutronium that makes up these stars? How does it manage to resist further collapse into a black hole? And what exotic physics governs the interior of an object where the laws of everyday matter simply cease to apply? That's what we'll explore next, as we delve deeper into the astonishing composition and structure of these ultimate cosmic cubes. Alright, dreamers, if you thought a sugar cube weighing 1 billion tons was mind-bending, prepare yourselves, because we're about to dive even deeper into the heart of a neutron star. In Chapter 1, we peeled back the layers of a collapsing star, watching as gravity crushed atoms, forcing electrons and protons to merge into neutrons, creating a dense neutron-rich core. We saw how this celestial crunch erased the very concept of empty space within matter, giving birth to a truly impossible object. But now, the real question emerges: what is this stuff, this neutronium we've been talking about, and what prevents it from collapsing endlessly, spiraling down into the ultimate abyss of a black hole? We're about to explore the exotic physics that turns a star's core into the universe's most formidable fortress against gravity. So, settle in, because your mind is about to happily ache with wonder once more. Imagine, if you will, the atoms that make up your hand, the screen you're looking at, even the air you breathe. They're mostly empty space, right? Tiny nuclei, vast electron clouds. Now, picture that star collapsing, gravity squeezing it tighter and tighter. The electron clouds are gone, the nuclei themselves are shattered. What's left is a cauldron of subatomic particles, primarily neutrons, packed so tightly that they are literally touching. This isn't just dense, in the way a brick is dense compared to a sponge. This is a new state of matter entirely, unlike anything we encounter on Earth. We call it neutron degenerate matter, or simply neutronium. Think of it like this. You're trying to cram as many people as possible into a tiny room. Eventually, you can't fit anymore. But what if those people were all highly individualistic, each demanding their own personal space, even if it's just a sliver? That's kind of what's happening with neutrons. They are subatomic particles called fermions. And fermions have a fundamental rule. No two identical fermions can occupy the exact same quantum state at the same time in the same place. This is famously known as the Pauli exclusion principle. Now, don't worry about the quantum mechanics too much. What it means for our neutron star is this. As gravity tries to force neutrons closer and closer, they resist. They push back. It's not a physical push in the way you'd push a door, but a quantum mechanical resistance, a fundamental refusal to be in the same spot as another neutron, with the same properties. This powerful internal pressure, born from the very fabric of quantum reality, is called neutron degeneracy pressure. It's the ultimate cosmic bouncer, preventing the party from getting too crowded. This pressure is what holds a neutron star up against the relentless, unimaginable force of its own gravity. It's a cosmic tug-of-war on a scale that defies imagination, and for a time the neutron degeneracy pressure wins. Consider its predecessor, the white dwarf star. White dwarfs are also incredibly dense, held up by electron degeneracy pressure. Electrons, like neutrons, are fermions, and they also resist being squeezed too tightly. But electrons are much lighter than neutrons. Imagine trying to stop a runaway train with a feather versus a brick wall. Electron degeneracy pressure is powerful, but it has its limits. If a white dwarf gains too much mass, exceeding about 1.4 times the mass of our Sun, the Chandrasekhar limit, electron degeneracy pressure fails, and the star collapses further, potentially forming a neutron star. Neutron degeneracy pressure, however, is a whole other beast. Because neutrons are so much more massive than electrons, their degeneracy pressure is vastly, almost incomprehensibly stronger. It's the universe's ultimate structural integrity, able to withstand gravitational forces that would crush anything else into oblivion. But even this incredible force has its breaking point. There's a limit to how much mass even neutron degeneracy pressure can support. This critical threshold is known as the Tolman-Oppenheimer-Volkoff TOV limit, and it's generally estimated to be around 2 to 2.5 times the mass of our Sun. If a collapsing stellar core exceeds this limit, if it's born from a star-sacked too massive, then even the might of neutron degeneracy pressure isn't enough. Gravity wins the cosmic tug-of-war, and the neutron star collapses further, past the point of no return, forming a black hole. So, a neutron star exists in this incredibly delicate balance. Massive enough to have crushed all atomic structure, but not quite massive enough to succumb entirely to the singularity of a black hole. It's a cosmic sweet spot, a truly unique and extreme object in our universe. Now, let's take a journey inside this extraordinary object. What does the interior of a neutron star look like? It's not uniform, it's a layered structure, each layer home to increasingly exotic and mind-boggling physics. Imagine peeling an onion, but this onion is made of the densest matter imaginable, and each layer reveals a new, extreme state of existence. The outer crust. Right beneath the surface, where the density is only a few million times that of water, still utterly insane, right? We find what's called the outer crust. Here, despite the immense pressure, some atomic nuclei still exist, though they're highly compressed and packed into a crystalline lattice, like a super dense solid. These nuclei are incredibly rich in neutrons, far more than you'd find in stable atoms on Earth. Electrons are still present here, forming a highly conductive, degenerate electron gas that permeates the lattice. It's a bizarre, super dense metallic environment. The inner crust. As we delve deeper, the pressure and density climb even higher. This is where things get truly wild. In the inner crust, the density reaches hundreds of millions of tons per cubic centimetre. Here, the nuclei begin to get so squashed and deformed that they take on incredibly strange and complex shapes. Scientists have dubbed these structures nuclear pasta. Can you picture it? Gravity is so intense that atomic nuclei are stretched and moulded into sheets, rods, and even intricate networks, resembling cosmic spaghetti, lasagna, gnocchi, or even Swiss cheese. Imagine long cylindrical spaghetti nuclei or flat lasagna sheets all packed together, suspended in a sea of free-moving neutrons. These neutrons are so dense and cold that they actually behave as a goop fluid, a frictionless fluid that can flow without any resistance, a quantum phenomenon. It's a state of matter so alien, so extreme, that it's almost beyond our everyday comprehension. The outer core. Pushing past the nuclear pasta, we enter the outer core. Here, the density skyrockets even further, reaching billions of tons per cubic centimetre. At this depth, the pressure is so immense that most of the nuclei have completely dissolved. What remains is primarily a soup of free neutrons, protons and electrons. The neutrons are still the dominant species, and they continue to form a superfluid, but now with a small percentage of protons and electrons mixed in. These protons and electrons might also form superconducting and superfluid states, respectively. That's right, frictionless flow and perfect electrical conductivity, all happening simultaneously in the heart of a dead star. The inner core. And finally, at the very centre, lies the inner core. The most mysterious and extreme region of a neutron star. The densities are truly staggering, potentially reaching 10 times that of an atomic nucleus. This is where our understanding gets hazy. where theoretical physics strains to keep up with reality. What kind of matter exists at these unfathomable pressures? Some theories suggest that the neutrons themselves might break down. They are, after all, made of even smaller particles called quarks. Could the inner core be a quark-gluon plasma? A state of matter where quarks and gluons, the particles that bind quarks together, are no longer confined within individual neutrons and protons, but instead flow freely in a super-hot, super-dense soup, similar to what the universe was like moments after the Big Bang. Or perhaps it's filled with exotic particles called hyperons, heavier cousins of neutrons and protons. The truth is, we don't fully know. The conditions in the inner core of a neutron star are so extreme that they are impossible to replicate in any lab on Earth. Studying this region is like trying to understand the deeper secrets of the universe, using only the faintest whispers from across the cosmos. It's a frontier of physics, a place where our most fundamental theories are put to the ultimate test. So a neutron star isn't just a ball of uniform, super-dense material. It's a cosmic marvel, a celestial onion with layers of increasingly bizarre and exotic states of matter, each pushing the boundaries of what we thought possible. From nuclear pasta to superfluid neutrons, from perfect conductors to a potential quark-gluon plasma, these objects are living laboratories of extreme physics. And it's this incredibly complex, layered structure, combined with the sheer power of neutron degeneracy pressure, that allows a neutron star to stand its ground against gravity's relentless embrace, preventing it from spiraling into the ultimate cosmic void. For now, it holds. But what happens when these cosmic fortresses are not just static objects, but dynamic, spinning, highly magnetic powerhouses? What observable phenomena do they create that allow us to detect them across vast cosmic distances? That, my friends, is a story for our next chapter, where we'll explore the incredible, often violent and always awe-inspiring lives of neutron stars as they interact with the universe around them. Don't forget to hit that like button, subscribe to Dreamy Science for more cosmic adventures, and let us know in the comments, which layer of the neutron star's interior blew your mind the most? Was it the nuclear pasta, the superfluid neutrons, or the mysterious quark-gluon plasma? We love hearing your thoughts. Until next time, keep looking up and keep dreaming big. Alright, dreamy science explorers, are you ready to pick up right where we left off? We've journeyed into the heart of a neutron star, peered into its mind-bendingly dense layers, and grappled with the quantum forces that keep it from collapsing into oblivion. We know it's a stellar corpse, a sphere of pure neutronium, with gravity so fierce it warps space-time around it. But here's the profound mystery we left hanging in the cosmic ether. How do we know these things exist? How do these invisible, super-dense giants born from the most violent stellar deaths announce their presence across unimaginable distances? If they don't emit much visible light, how do we observe them? The answer, my friends, lies in two of their most spectacular and extreme properties, their spin and their magnetism. These aren't just ordinary rotations or everyday magnetic fields. These are cosmic forces dialed up to 11, turning neutron stars into some of the most dynamic and observable phenomena in the universe. Get ready to have your mind happily ache with wonder, because we're about to uncover the secrets of pulsars and magnetars. The cosmic spinner. Why neutron stars rotate so fast. Let's start with the spin. Imagine a figure skater gracefully twirling on ice. When she extends her arms, she spins relatively slowly. But as she pulls her arms in close to her body, what happens? She spins incredibly fast, right? This isn't magic, it's a fundamental law of physics called the conservation of angular momentum. Simply put, if an object is rotating, its rotational inertia, how its mass is distributed relative to its axis of rotation, and its speed of rotation are linked. If its mass distribution shrinks, its spin speed has to increase to conserve that angular momentum. Now, apply this principle to a star. Before its catastrophic collapse, the massive progenitor star, the one that was 8 to 20 times the mass of our Sun, was already rotating. Perhaps not super fast, maybe once every few days or weeks, like our own Sun. It was a gargantuan sphere, hundreds of thousands, even millions of miles across. But when that star runs out of fuel and its core collapses, what happens? That massive amount of stellar material, once spread out over a vast volume, is now crushed down into a sphere only about 12 miles, 20 kilometers across. Think about that. Something the size of a city containing more mass than our entire Sun. Just like our figure skater pulling in her arms, this incredible shrinkage causes the neutron star to spin at an absolutely astonishing rate. We're not talking about a leisurely rotation here. We're talking about hundreds of rotations per second. Yes, you heard that correctly. Some neutron stars complete a full revolution faster than a helicopter rotor blade spins. Imagine the forces at play. If you could stand on the surface of such an object, which, spoiler alert, you absolutely could not, you'd be flung off at an incredible fraction of the speed of light. This rapid, relentless spin is one of the key ingredients in making neutron stars observable. The magnetic monster. Fields beyond imagination. Next, let's talk about magnetism. Our Earth has a magnetic field relatively weak, but strong enough to guide compasses and protect us from solar winds. Our Sun has a magnetic field much stronger that causes sunspots and solar flares. But neutron stars, their magnetic fields are on an entirely different level. Just like angular momentum, magnetic flux is also conserved during the stellar collapse. The progenitor star had its own magnetic field weaving through its vast volume. When that star collapses, all those magnetic field lines, once spread out, are squeezed into an incredibly tiny sphere. It's like taking all the magnetic power of a football stadium-sized magnet and crushing it down into a tiny marble. The result? An amplification of the magnetic field to unimaginable strengths. How strong are we talking? While Earth's magnetic field is about 0.5 Gauss, and a powerful refrigerator magnet is around 100 Gauss, a typical neutron star's magnetic field is in the range of trillions of Gauss. And some, the most extreme, can reach quadrillions of Gauss. To put that into perspective, if you were to bring a neutron star within 1,000,000 miles of Earth, its magnetic field would be strong enough to wipe every credit card, every hard drive, every electronic device on our planet clean. It would rip the iron out of your blood. It would distort atoms themselves, making them elongated and strange. This isn't just a strong magnet. It's a fundamental force of nature unleashed. These super strong magnetic fields are the second crucial ingredient in how we detect these cosmic titans. And pulsars, the universe's lighthouses. Now, let's put these two extreme properties together. Rapid spin and immense magnetism. This combination gives us one of the most iconic and fascinating objects in the cosmos, pulsars. A pulsar is a type of rapidly rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. Here's the kicker. The magnetic axis of the neutron star is usually not aligned with its rotational axis. Imagine a tilted top spinning incredibly fast. As the neutron star spins, these powerful magnetic fields accelerate charged particles, electrons and positrons, away from the magnetic poles, creating incredibly bright focused beams of radiation. These beams are like the searchlight from a cosmic lighthouse. And just like a lighthouse beam sweeping across the ocean, if one of these beams happens to sweep across our line of sight here on Earth, we detect a precise regular pulse of radiation. These pulses were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, who initially nicknamed them Little Green Men, because their regularity was so uncanny they thought they might be alien signals. Of course, we now know they are the natural consequence of rapidly spinning, highly magnetized neutron stars. Pulsars emit across the electromagnetic spectrum, from radio waves to X-rays and even gamma rays. The regularity of their pulses is astounding. Some are more precise than the best atomic clocks on Earth. This incredible precision makes them invaluable tools for astronomers, allowing us to test theories of gravity, detect gravitational waves from binary pulsar systems, and even measure the interstellar medium. There are even millisecond pulsars, which are neutron stars that have been recycled in binary systems, siphoning off matter from a companion star and spinning up to hundreds of times per second, becoming even more precise cosmic timekeepers. Magnetars, the universe's magnetic monsters. But what about those neutron stars with truly mind-boggling magnetic fields, the quadrillions of Gauss monsters we mentioned earlier? These are a special, even more extreme class of neutron stars called magnetars. Magnetars represent the pinnacle of cosmic magnetism. Their fields are so incredibly powerful that they can literally crack the star's solid crust, causing what we call starquakes. Think of it like an earthquake on Earth, but instead of tectonic plates shifting, it's the super dense, rigid crust of a neutron star fracturing under immense magnetic stress. When a starquake occurs, it unleashes an incredible amount of energy in a fraction of a second, often in the form of powerful bursts of X-rays and gamma rays. These events are so energetic that they can be detected across billions of light years. We classify these events into two main types: soft gamma repeaters, SGRs, which emit sporadic bursts of soft gamma rays and hard X-rays, and anomalous X-ray pulsars, XPs, which are X-ray pulsars whose energy output can't be explained by their spin down alone, suggesting a magnetic origin. The magnetic field of a magnetar is so strong that it can even affect the very fabric of matter and light around it. Atoms near a magnetar would be stretched into bizarre, elongated shapes. The vacuum of space itself might become polarized. If you were to somehow get close to a magnetar, its magnetic field would literally tear you apart at the molecular level. It's a truly terrifying and awe-inspiring force. The formation of these ultra-strong fields is still a topic of active research, likely involving rapid rotation and a powerful dynamo effect in the early hot life of the neutron star. Beyond the beams. Other dynamic phenomena. Beyond their lighthouse beams and the magnetic outbursts, neutron stars display other fascinating dynamics. Sometimes pulsars experience sudden, unexpected spin-ups called glitches. These are thought to occur when the rapidly spinning superfluid interior of the neutron star, remember that soup of neutrons we talked about, transfers some of its angular momentum to the solid outer crust, causing a sudden, tiny acceleration. It's like a cosmic burp, a sudden adjustment in their internal mechanics. These incredible objects, born from the death throes of massive stars, are far from inert stellar remnants. They are dynamic, extreme, and profoundly influential. They are the universe's most powerful magnets, its most precise clocks, and its most energetic cosmic lighthouses. They are a testament to the fact that even in death, a star can achieve a new, spectacular form, revealing itself through forces that defy our everyday understanding. So the next time you look up at the night sky, remember those tiny, invisible points of light that aren't quite stars. Remember the incredible story of the neutron star, a true marvel of the universe, silently broadcasting its existence through its furious spin and unparalleled magnetism. What do you find most mind-boggling about these spinning magnetic monsters? Share your thoughts in the comments below. And if you're enjoying this journey into the extreme, don't forget to like this video, subscribe to Dreamy Science for more cosmic adventures, and hit that notification bell so you don't miss our next chapter. We appreciate every single one of you from every corner of our amazing planet. Keep dreaming big and keep exploring the wonders of science. Welcome back, cosmic explorers, to Dreamy Science. If you've been with us since the beginning, your mind is probably already happily aching with wonder. We've journeyed deep into the heart of neutron stars, those impossibly dense cosmic remnants, and marveled at their incredible structure, their mind-bending magnetism, and their role as the universe's most precise pulsars and most powerful magnetars. We've seen them as isolated, extreme objects silently, or not so silently, spinning through the void. But what if I told you that these stellar zombies don't always fly solo? What if I told you that sometimes they find a partner, or even collide with one, creating some of the most spectacular universe-altering events we've ever witnessed? Get ready, because today we're diving into the dynamic, dramatic, and utterly crucial role neutron stars play in the grand cosmic ballet. We're talking about gravitational tugs of war, cosmic feeding frenzies, and explosions that literally forge the gold on your finger. The cosmic dance, neutron stars in binary systems. You see, our sun is a bit of an anomaly. More than half of all stars in the Milky Way aren't solitary wanderers like our home star. They are part of multi-star systems, often binaries, where two stars orbit a common centre of mass. And just like their more conventional stellar brethren, neutron stars often find themselves in these intricate celestial dances. Imagine a neutron star, a tiny, super-dense sphere, maybe 12 miles across, locked in a gravitational embrace with a much larger normal companion star, perhaps a red giant or a main sequence star, hundreds of thousands of miles wide. It's like a cosmic David and Goliath, except David has the gravitational pull of 1,000 suns packed into a city-sized ball. What happens in such a system? Well, the neutron star's immense gravity doesn't just hold its companion in orbit, it actively pulls on its outer layers. If the companion star gets too close, or if it swells up as it ages, the neutron star becomes a cosmic vacuum cleaner, siphoning off gas from its unfortunate partner. We call these fascinating pairings X-ray binaries, and they are truly spectacular. Picture this. Gas from the companion star, rich in hydrogen and helium, is ripped away by the neutron star's powerful gravitational field. But it doesn't just fall straight in. Oh no, the universe is far too elegant for that. Due to the conservation of angular momentum, that same principle that makes an ice skater spin faster when they pull their arms in, this stolen gas doesn't simply plummet. Instead, it forms a vast, swirling whirlpool around the neutron star, a superheated or accretion disk that can be many times larger than the neutron star itself. This disk is a maelstrom of activity. As the gas spirals ever closer to the neutron star, friction and gravitational forces heat it to unimaginable temperatures, millions of degrees Celsius. At these extreme temperatures, the gas doesn't just glow. It emits powerful bursts of X-rays, gamma rays, and even jets of particles shooting out into space. This is how we detect these systems, often as some of the brightest X-ray sources in the galaxy. They are literally screaming their presence across the cosmos in high-energy light. But the story doesn't end there. As this superheated matter eventually falls onto the neutron star's surface, it does something incredible. It transfers its angular momentum to the neutron star, effectively spinning it up. Remember how pulsars spin hundreds of times per second? Well, through this process of accretion, some neutron stars get spun up to truly mind-boggling rates, reaching rotations of hundreds of times per second, sometimes over 700 rotations per second. These are known as millisecond pulsars, or recycled pulsars, because they've been recycled into incredibly fast spinners by their companions' offerings. They become the fastest, most precise clocks in the universe, even more so than their younger counterparts. It's a cosmic spin class, powered by gravity and gas, and it gives us some of the most stable timekeepers in existence. So while some neutron stars are solitary lighthouses, others are voracious feeders, locked in a gravitational tango that fuels some of the most energetic phenomena in the galaxy. But what happens when the dance gets too close? What happens when two of these extreme objects, these super dense remnants, finally meet their match? The ultimate collision, neutron star mergers. Imagine not one but two neutron stars, perhaps born together in a binary system, or perhaps gravitationally captured by each other over billions of years. They orbit each other, gradually losing energy through the emission of gravitational waves, ripples in the very fabric of space-time itself, predicted by Albert Einstein over a century ago. For eons, they spiral inward, slowly, inexorably, drawn together by the irresistible force of their mutual gravity. But as they get closer, their orbital speed increases dramatically. The dance accelerates, becoming a frantic, dizzying waltz of death. In the final moments, they are whipping around each other hundreds of times per second, moving at a significant fraction of the speed of light. And then it happens. A cataclysmic, universe-shaking event. They collide. This isn't just a bump in the night. It's the most powerful explosion since the Big Bang, a cosmic spectacle of unimaginable violence and profound creation. When two neutron stars merge, the energy released is staggering. For a fleeting moment, they become one of the brightest objects in the universe, an event we call a kilonova. Think about that for a second. We're talking about an explosion that's 1,000 times brighter than a typical nova, though still dimmer than a full-blown supernova. But the light we see, the electromagnetic radiation, is just one piece of the puzzle. The first hint of such an event came not from light, but from those elusive ripples in space-time, gravitational waves. On August 17, 2017, the LIGO and Virgo observatories designed to detect these tiny ripples simultaneously picked up a signal unlike any they had seen before. It was the distinct chirp of two massive objects spiraling into each other, culminating in a final powerful burst. This signal, designated GW0817, was the first direct detection of a neutron star merger, and then, just 1.7 seconds later, telescopes across the globe detected something else, a flash of gamma rays, followed by a rapidly fading glow across the electromagnetic spectrum, from X-rays to ultraviolet, visible light, infrared, and radio waves. This was the kilonova, the electromagnetic counterparts of the gravitational wave signal. It was the first time we'd ever observed a cosmic event with both gravitational waves and light, opening a brand new window into the universe. But here's where it gets truly mind-bending, truly profound. When these two neutron stars collide, they don't just explode, they become the universe's ultimate alchemists. The extreme conditions created during the merger, unfathomable temperatures, densities, and an overwhelming abundance of free neutrons trigger a process called rapid neutron capture, or the OR process. Imagine this: a vast amount of neutron-rich material ejected at incredible speeds during the collision is bombarded by free neutrons. Atomic nuclei rapidly absorb these neutrons, becoming super heavy and unstable. They then undergo radioactive decay, transforming into stable, incredibly dense elements. And what elements are forged in this cosmic crucible? I'm talking about the heaviest elements in the periodic table. We're talking about gold, we're talking about platinum, we're talking about uranium, lead, silver, and countless other elements that are essential to our technology, our jewelry, and even the very structure of our planet. Every single atom of gold on Earth, every platinum ring, every piece of uranium fuel, likely owes its existence to the titanic collision of two neutron stars billions of years ago. You are literally wearing the remnants of a neutron star merger. Isn't that absolutely astonishing? These extreme violent events are not just destructive, they are the universe's ultimate creative forces, seeding the cosmos with the building blocks of complexity, life, and luxury. What's left after such a merger? The outcome depends on the combined mass of the two neutron stars. If the resulting object is below the Tolman-Oppenheimer-Volkoff-Tovey limit, that critical threshold we discussed for neutron star stability, it might form an even larger, faster spinning neutron star. But more often, if the combined mass exceeds that limit, the newly merged object collapses completely, forming something even more mysterious and extreme, a brand new black hole. A black hole that was just born from the death and fusion of two of the universe's densest objects. So, from solitary lighthouses to cosmic vacuum cleaners, and finally to the ultimate alchemists forging the very elements of our world, neutron stars are far more than just stellar remnants. They are dynamic, interacting players in the grand cosmic drama, shaping the universe in ways we are only just beginning to understand. They are the densest objects in the universe, yes, but they are also the most profound engineers, silently, violently creating the very matter that makes up everything around us. What do you think about these cosmic collisions? Does it blow your mind to think the gold on your finger was forged in such an extreme event? Let us know in the comments below. And if you're as amazed by these cosmic wonders as we are, don't forget to like this video, subscribe to Dreamy Science for more mind-bending journeys, and share it with anyone who loves to stare up at the night sky and wonder. Because the universe, my friends, is always full of surprises, and we're just getting started. Those lingering questions about the neutron star's mysterious inner core and the genesis of magnetar's ultra-powerful fields aren't roadblocks, friends. No, they are invitations, urgent, compelling calls from the cosmos itself, challenging us, pushing us to build bigger, better, more imaginative tools to pierce the veil of cosmic obscurity. They remind us that the universe is a vast library, and we've only just begun to turn the first few pages. So how do we, mere inhabitants of a tiny blue marble, even begin to investigate objects so distant, so dense, so utterly extreme? We do it with ingenuity, with persistence, and with an ever-expanding array of cosmic senses. Imagine trying to understand a complex machine when you can't touch it, can't even get close to it. You have to rely on every flicker, every hum, every vibration it emits. That's precisely what astronomers do with neutron stars. We listen, we watch, we measure, using every facet of the universe's language. Our primary tools for centuries have been telescopes, collecting light across the electromagnetic spectrum. For neutron stars, this means we're not just looking for visible light, which is rare and faint from these compact objects. Instead, we tune into the high-energy wavelengths. X-ray telescopes like NASA's Chandra and ESA's XMM Newton are crucial. They detect the incredibly hot, energetic radiation pouring from the surfaces of neutron stars, the fierce glow of accretion disks around them in X-ray binaries, and the violent bursts from magnetars. These X-rays are like the fiery breath of these cosmic dragons, telling us about their extreme temperatures and the dynamic processes unfolding at their boundaries. Then there are gamma-ray telescopes, peering into the highest energy reaches, catching the most extreme phenomena. When a magnetar unleashes a starquake, those earth-shattering events we talked about, they often manifest as powerful bursts of gamma rays, momentary cosmic beacons that momentarily outshine entire galaxies. These gamma-ray bursts are fleeting but telltale signs of the most energetic explosions in the universe, often hinting at the birth or violent demise of neutron stars. But perhaps the most iconic way we've heard from neutron stars is through radio waves. Remember our cosmic lighthouses, the pulsars? Radio telescopes like the Arecibo Observatory before its sad collapse, or the mighty Green Bank telescope, are designed to catch those incredibly precise rhythmic pulses of radio waves. Each pulse is a tick-tock from a rapidly spinning neutron star, a cosmic clock telling us about its rotation period, its magnetic field, and even helping us test Einstein's theory of general relativity with exquisite precision. Imagine being able to measure the tiny wobble of a distant star, or the slight slowing of its spin over millennia, all from radio signals that have travelled light years to reach us. It's an incredible feat of cosmic eavesdropping. However, the universe speaks in more than just light. As we ventured into the 21st century, humanity opened an entirely new window onto the cosmos: gravitational wave astronomy. We talked about GWMT 817, the groundbreaking detection of two neutron stars colliding. This wasn't just another observation, it was a revolution. Before LIGO and Virgo, we could only infer these events from the light they emitted. Now we could hear the very fabric of space-time ripple and stretch as these titanic objects spiraled into their cataclysmic embrace. Think of it this way: electromagnetic waves are like ripples on the surface of a pond, carrying information about what's on the surface. Gravitational waves are like disturbances within the pond itself, telling us about the deep fundamental movements of the water. They offer a direct probe into the most violent events in the universe, events so extreme that light itself can get trapped or obscured. Gravitational waves cut through everything, carrying pristine information about the masses, spins, and orbital dynamics of the merging neutron stars. They are the universe's ultimate seismic sensors. The detection of GW70817 wasn't just about confirming a theory, it was about connecting the dots in a way we never thought possible. For the first time, we observed an event with both gravitational waves and electromagnetic radiation, a multi-messenger astronomy triumph. The gravitational wave signal told us about the merger itself, the masses and the final moments of the dance. The light signals, from radio waves to gamma rays, told us about the kilonova explosion, the heavy element production, and the aftermath. It was like finally getting to watch a movie with both picture and sound, when before we only had one or the other. This synergy is key to unravelling the deepest secrets of neutron stars and their role in cosmic evolution. But what about the future? Our current understanding, while profound, is still just the tip of the cosmic iceberg. The next generation of observatories promises to plunge us even deeper into the mysteries of these dense objects. On the electromagnetic front, projects like the Square Kilometre Array, SKA, will be vastly more sensitive radio telescopes, capable of detecting fainter pulses across greater distances, potentially revealing new populations of neutron stars and allowing us to map their distribution in our galaxy and beyond with unprecedented detail. New X-ray observatories like ESA's proposed Athena mission will offer higher resolution and sensitivity, giving us clearer pictures of neutron star surfaces, accretion disks, and the enigmatic nuclear pasta within their crusts. And in the realm of gravitational waves, the future is even more exciting. Current detectors like LIGO and Virgo are already being upgraded, but the real game changers will be next-generation instruments like Cosmic Explorer in the US and the Einstein Telescope in Europe. These will be significantly larger and more sensitive, capable of detecting neutron star mergers from much further across the universe and with greater precision. Imagine not just detecting a merger, but being able to pinpoint its location with incredible accuracy, allowing us to rapidly point our light-based telescopes to catch the kilonova glow almost instantly. This will drastically increase our chances of observing more multi-messenger events, providing a deluge of data that will surely revolutionize our understanding of heavy element formation, the equation of state of ultra-dense matter, and the very limits of neutron star existence. Beyond light and gravity, there's another cosmic messenger patiently waiting for its moment in the spotlight: neutrinos. These ghostly particles, which interact so weakly with matter, are produced in immense quantities during supernova explosions, the very birth cries of neutron stars. While detecting neutrinos from supernovae is incredibly challenging, we've only managed it once, from SN 1987A, future neutrino observatories could potentially provide direct information about the core collapse process itself, giving us an unparalleled view into the moment when a star's core transforms into a neutron star. What happens during those milliseconds of collapse? How does the nascent neutron star cool? Neutrinos hold the answers, waiting for us to develop the technology to see them. The study of neutron stars isn't just about building bigger telescopes or more sensitive detectors, it's also about pushing the boundaries of theoretical physics and computational power. Supercomputer simulations are becoming incredibly sophisticated, allowing scientists to model the extreme physics of neutron star mergers, the intricate dynamics of their interiors, and the behavior of matter under conditions that simply cannot be replicated in any lab on Earth. These simulations are our virtual laboratories, letting us explore what-if scenarios and test hypotheses about the inner core's composition, whether it's exotic quark-gluon plasma or something even stranger. And let's not forget the nuclear physicists. Experiments on Earth, using particle accelerators, are trying to recreate, however briefly, the conditions of neutron-rich matter. By studying how nuclei interact and how neutrons behave at extreme densities, these experiments provide crucial input for the equation of state that governs a neutron star's interior. It's a beautiful symbiotic relationship. Astrophysicists observe the cosmos, nuclear physicists probe the fundamental forces, and theoretical physicists weave it all together into a coherent picture. So why does all this matter? Why do we happily ache with wonder over these cosmic behemoths, these dense, spinning, magnetic marvels? Because neutron stars are more than just fascinating objects. They are cosmic laboratories where the most extreme physics in the universe plays out. They are the ultimate proving grounds for our theories of gravity, matter, and the fundamental forces. Understanding neutron stars means understanding the limits of matter itself. What happens when you crush atoms until they literally cease to exist in their familiar form? What new states of matter emerge? The answers to these questions are not just academic. They inform our understanding of how the universe works at its most fundamental level. They are also the universe's ultimate alchemists, responsible for forging the elements that make up our world, our bodies, and the gold on your finger. Without neutron star mergers, the periodic table would be a much shorter, less interesting place. They remind us of our deep, intimate connection to the cosmos, that the very atoms we are made of were once forged in the heart of a dying star or in the explosive collision of two others. And perhaps most profoundly, the study of neutron stars is a testament to human curiosity and ingenuity. It's about our insatiable drive to explore, to understand, to push the boundaries of what we know. Each new discovery, each new piece of the puzzle, not only expands our knowledge but also humbles us, reminding us of the vastness and complexity of the universe we inhabit. So, as we look to the future, with new observatories reaching for fainter signals and new theories pushing the limits of our imagination, we can be sure of one thing. The neutron star will continue to be a beacon of wonder, a cosmic challenge that inspires generations of scientists and stargazers alike. It's a journey into the heart of density, into the very fabric of space-time, and into the profound questions of existence itself. What mysteries do you think the next decade of neutron star research will unveil? What questions about these cosmic titans burn brightest in your mind? Let us know in the comments below, and don't forget to like this video and subscribe to Dreamy Science for more mind-bending journeys into the cosmos. Until next time, keep looking up, keep wondering, and keep dreaming big. Our journey into the heart of neutron stars, these cosmic behemoths of density, has revealed a universe far stranger and more extreme than we could ever imagine. We've peered into their layered interiors, marvelled at their furious spins and magnetic might, and witnessed their cataclysmic interactions. But as we stand at the precipice of current understanding, we realise that the most profound mysteries still beckon, drawing us deeper into the unknown. Remember how we talked about neutron stars being cosmic laboratories? Well, that's not just a poetic phrase, it's the absolute truth. These objects are not merely fascinating subjects of study, they are nature's ultimate particle accelerators, gravity wells, and magnetic field generators operating at scales and energies utterly impossible to replicate in any terrestrial lab. They are our best, and often only, chance to test the fundamental laws of physics under conditions that push our theories to their breaking point. One of the most tantalizing and perhaps frustrating mysteries we face is the precise equation of state for ultra-dense matter. What does that even mean, you ask? Imagine you have a material, and you want to describe how it behaves under different pressures and temperatures. Does it compress easily? Does it resist? Does it change its fundamental nature? That description is its equation of state. Now apply that to the matter inside a neutron star, where a sugar cube's worth weighs 1 billion tons. We know it's neutronium mostly, but what about the inner core? Is it still just neutrons, or has the pressure become so immense that the neutrons themselves have broken down into their fundamental constituents, quarks and gluons, forming a quark-gluon plasma? Or perhaps it's a soup of exotic hyperons, stranger baryons made of heavier quarks. The truth is, we don't know for sure. It's like trying to deduce the exact recipe and texture of a cake by only seeing its shadow and measuring its weight, without ever tasting or touching it. The conditions are so extreme, so far beyond anything we can create on Earth, that our theoretical models struggle to keep up. This isn't just an academic exercise. Understanding the equation of state is critical because it dictates everything about a neutron star, its maximum mass, its radius, how it vibrates, and even how it cools. A stiffer equation of state, meaning the matter resists compression more strongly, would result in larger neutron stars for a given mass. A softer one would mean smaller, more compact stars. So how do we solve this cosmic riddle? We're tackling it from multiple angles, combining ingenious observations with cutting-edge theoretical physics. One of our most powerful tools is the ability to measure the masses and radii of neutron stars with increasing precision. Missions like NASA's NISA, Neutron Star Interior Composition Explorer, mounted on the International Space Station, are revolutionizing this. NISA observes X-rays emitted from the surface of neutron stars. By carefully analyzing how these X-rays are affected by the star's immense gravity and how the star's rotation sweeps these emissions across our detectors, scientists can infer the star's radius. Imagine trying to measure the size of a rapidly spinning, incredibly dense object thousands of light years away, just by watching the light it emits. It's an incredible feat of engineering and physics, but it's not just X-rays. Gravitational wave astronomy, which we discussed with neutron star mergers, provides another crucial piece of the puzzle. When two neutron stars spiral into each other, their immense gravity causes them to deform each other, like cosmic tidal forces pulling and stretching. This deformation, known as tidal deformability, leaves a subtle but detectable signature in the gravitational waves emitted during the merger. A stiffer neutron star resists deformation more, while a softer one is easier to stretch. By analysing the gravitational wave signal, like the one from GW 170817, we can place constraints on this tidal deformability, which in turn helps us narrow down the possible equations of state. It's like listening to the cosmic chirp of the merger and discerning the physical properties of the merging objects from the sound itself. It's truly mind-bending. Then there's the enigma of magnetars. We know they possess the most powerful magnetic fields in the universe, quadrillions of Gauss, strong enough to rip you apart at an atomic level from 1,000 miles away. But how do these fields get generated? The leading theory involves a dynamo mechanism operating within the rapidly rotating convective interior of the newly formed neutron star. Think of it like Earth's magnetic field, but amplified to an insane degree, fueled by the exotic, super-dense and often superfluid matter inside. The challenge is understanding the interplay between extreme rotation, convection in a fluid of superfluid neutrons and superconducting protons, and the initial magnetic field of the progenitor star. It's a complex dance of electromagnetism and hydrodynamics on a cosmic scale. When a magnetar experiences a starquake, a sudden release of stress in its crust due to magnetic field reconfiguration, it sends out powerful bursts of X-rays and gamma rays, which we detect. By studying these unpredictable fleeting events, we gain clues about the internal structure and magnetic field dynamics. Cracking the magnetar code would not only solve a major astrophysical mystery, but also deepen our understanding of fundamental electromagnetism in environments that stretch our current theories to their limits. And what about the very birth of these incredible objects? The core collapse supernova, the cataclysmic explosion of a massive star, is not just the end of a star's life, but the violent genesis of a neutron star. Yet despite decades of research, the precise mechanism that drives these explosions remains one of astrophysics' biggest challenges. It's like watching a balloon pop and knowing something caused it, but not precisely understanding the pressure dynamics and material stresses that led to the rupture. The prevailing theory is the neutrino mechanism. During the core collapse, an incredible torrent of neutrinos is produced. These ghostly particles, which rarely interact with matter, are thought to deposit just enough energy in the outer layers of the collapsing star to reverse the infall and drive the spectacular explosion we observe. Imagine a tiny whisper of energy, multiplied by quadrillions of neutrinos, turning a collapse into an outward explosion. It's an incredibly subtle and powerful process. Neutrinos are not just important for the explosion, they also play a crucial role in the cooling of a neutron star. Immediately after its birth, a neutron star is incredibly hot, and it sheds much of its thermal energy by emitting neutrinos. Observing these neutrinos from a newly formed neutron star in a supernova would be a game changer. It would allow us to directly probe the conditions in the heart of a collapsing star and the interior of a newborn neutron star. This is where neutrino astronomy comes in. Facilities like the Deep Underground Neutrino Experiment DUNE or IceCube are designed to detect these elusive particles, and while detecting neutrinos from a galactic supernova is rare, it holds immense promise for the future. Furthermore, the birth of a neutron star in a supernova might also produce a detectable gravitational wave signature. As the core collapses and bounces, and as the nascent neutron star rapidly rotates and potentially deforms, it could emit gravitational waves. Detecting these birth cries of neutron stars would offer an unprecedented window into the heart of a supernova, complementing our observations with light and neutrinos. It's the ultimate multi-messenger symphony of cosmic violence. All these lines of inquiry, from mass radius measurements to gravitational waves, from X-ray bursts to neutrino detection, are converging on the same goal: to understand the most extreme matter in the universe. Are we on the verge of discovering a new phase of matter, like the quark-gluon plasma, locked away in the inner cores of these stars? If so, it would be a monumental discovery, not just for astrophysics, but for particle physics. pushing the boundaries of our understanding of the fundamental building blocks of reality. It would mean that the universe itself is a giant laboratory, not just for us to observe, but to reveal entirely new physics. The future of neutron star research is incredibly bright, fueled by new technologies and a growing spirit of multi-messenger astronomy. We're not just looking up with optical telescopes anymore. We're listening with gravitational wave detectors, feeling with neutrino observatories, and peering through the universe with X-ray and gamma-ray satellites. Next-generation instruments, like the proposed Athena X-ray Observatory, or the ground-based Cosmic Explorer, and Einstein Telescope, for gravitational waves, promise even greater sensitivity and detail. They will allow us to probe deeper into the mysteries, to catch more elusive signals, and to refine our models with unprecedented precision. Neutron stars are more than just dead stars. They are living, breathing cosmic puzzles that challenge our deepest scientific assumptions. They are the ultimate test beds for Einstein's general relativity, for the theory of strong nuclear force, quantum chromodynamics, and for our understanding of matter itself. They are the bridges between the macroscopic world of gravity and the microscopic world of quantum mechanics, forcing us to confront the limits of our current theories. So as we bring this chapter to a close, remember that the story of neutron stars is far from over. It's an ongoing saga of discovery, driven by human curiosity and the sheer wonder of the cosmos. Every measurement, every detected ripple in space-time, every burst of X-rays brings us a step closer to unlocking their profound secrets. And in doing so, we not only understand these incredible objects better, but we also gain deeper insights into the fundamental laws that govern our entire universe. What mysteries do you think are the most exciting to unravel? What questions do neutron stars spark in your mind? Share your thoughts below. Your engagement fuels our collective journey of discovery. Don't forget to like this video, subscribe to Dreamy Science for more cosmic adventures, and hit that notification bell so you don't miss our next deep dive into the universe's most mind-bending phenomena. Because together, we continue to explore, to question, and to happily ache with wonder at the incredible universe we call home. We've journeyed through the mind-bending world of neutron stars, from their violent births to their extreme properties, from cosmic lighthouses to the universe's ultimate alchemists. We've seen how these stellar remnants challenge our imagination and push the boundaries of physics. But here's the most exciting part, the part that keeps us, at Dreamy Science, happily aching with wonder. The deepest mysteries of neutron stars are still waiting to be unraveled. And you, our curious cosmic explorers, are here at the precipice of discovery with us. Remember those three big questions we just touched on? The precise equation of state for ultra-dense matter, the genesis of magnetar's ultra-powerful magnetic fields, and the precise mechanism driving core collapse supernovae. These aren't just academic curiosities, they are the keys to unlocking fundamental secrets about matter, gravity, and the very fabric of our universe. And it's the first one, the equation of state, that truly holds the neutron star's deepest secret. The ultimate enigma, the equation of state. Imagine, if you will, a cosmic riddle wrapped in an enigma, encased in a super dense shell. That's the equation of state for neutron stars. What is it exactly? In simple terms, it's a mathematical relationship that describes how matter behaves under extreme conditions, specifically how much pressure it exerts at a given density. For everyday stuff like the air you breathe or the water you drink, we know these equations well. But when you compress matter to the point where a teaspoon weighs 1 billion tons, where atomic nuclei are crammed together tighter than anything we can replicate on Earth, all bets are off. Why is this so incredibly hard to pin down? Think about it. We're talking about densities that exist only in the hearts of collapsing stars, conditions so extreme they defy our terrestrial laboratories. We can't just scoop up a sample of neutron star core and run tests on it. So physicists resort to theoretical models, quantum chromodynamics calculations, and educated guesses, each attempting to predict how neutrons, protons, electrons, and potentially even more exotic particles would interact under such immense gravitational pressure. The stakes, they couldn't be higher. The equation of state is the fundamental blueprint of a neutron star. It dictates everything: its exact size for a given mass, how squishy or rigid is it, the maximum mass it can achieve before collapsing into a black hole, that TOV limit we talked about, and most thrillingly, what exotic forms of matter might be lurking in its innermost core. Is it just a sea of neutrons? Or does it harbour something truly alien, something we've never seen before? The answer to these questions lies buried within that elusive equation. Reading the cosmic fingerprints, observational clues. Thankfully, we are not entirely in the dark. The universe, in its infinite generosity, provides us with cosmic fingerprints, observational data that we can use to test and refine our theoretical models. This is where multi-messenger astronomy truly shines, allowing us to combine different types of cosmic signals to paint a more complete picture. First, let's talk about our mass and radius. Imagine you have a ball. If you know how much it weighs and how big it is, you can start to infer what it's made of and how tightly packed that material is. It's the same for neutron stars, but on a cosmic scale. Different proposed equations of state predict different mass-radius relationships. Some equations might suggest a smaller, denser star for a given mass, while others might predict a larger, puffier one. This is precisely what missions like the Neutron Star Interior Composition Explorer, NICER, are designed to measure. Orbiting the Earth, NICER uses its X-ray telescopes to observe the pulsations from rapidly pending neutron stars, particularly those in X-ray binaries. By carefully analysing the X-ray light curves, how the brightness changes over time, and the spectral information, scientists can map the hotspots on the neutron star's surface. As the star rotates, these hotspots appear and disappear, and the way their light is distorted by the star's immense gravity, gravitational lensing, provides a direct way to infer its mass and, critically, its radius. Every millimetre of precision in these measurements brings us closer to ruling out some equations of state and confirming others. It's like having a cosmic caliper, measuring the universe's densest objects with incredible accuracy. But that's not all. Remember the spectacular neutron star mergers we discussed, like GW17081? Those events offer another, equally profound window into the equation of state: tidal deformability. Picture two neutron stars spiralling closer and closer, their colossal gravitational fields stretching and pulling at each other like cosmic taffy. How much they squish and deform before they merge, their tidal deformability, is directly dependent on their internal structure and, you guessed it, their equation of state. If a neutron star is very stiff, like a super hard marble, it won't deform much under the gravitational strain. If it's a bit softer, like a cosmic stress ball, it will stretch more. This squishiness leaves an imprint on the gravitational waves emitted during the merger. Future, more sensitive gravitational wave detectors like a Cosmic Explorer and the Einstein telescope will be able to detect these subtle nuances in the gravitational wave signal with even greater precision. By measuring how much these stars give under the extreme tidal forces, we gain unprecedented insight into the pressure-density relationship within their cores. It's like feeling the texture of an object without ever touching it, just by listening to the ripples it creates in space-time And let's not forget the role of supernova neutrinos. While more indirect, observing the neutrinos emitted during a core collapse supernova, the very birth event of a neutron star, could also offer crucial clues. These ghostly particles carry information about the conditions deep within the collapsing stellar core, telling us about the density and temperature at the moment of neutron star formation. Future neutrino observatories like Hot Dune and IceCube are poised to capture these ephemeral messengers, potentially unveiling the initial conditions that set the stage for the neutron star's entire existence. It's like getting a birth announcement that also includes the baby's genetic code. Peering into the unseen core, exotic matter. Now, here's where the real excitement builds, where science fiction flirts with scientific reality. If we can truly pin down the equation of state, if we can understand how matter behaves at these mind-boggling densities, what might we find lurking in the neutron star's inner core? We've already touched on the possibility of quark-gluon plasma. Imagine a state where the individual neutrons and protons, normally distinct particles made of 3 quarks each, break down. Their constituent quarks and gluons, the fundamental particles that bind them, are no longer confined but roam freely in a sea of super hot, super dense matter. This is the state thought to have existed just microseconds after the Big Bang, and it might be recreated in the heart of a neutron star if the pressure is extreme enough. Finding evidence of quark-gluon plasma would be a monumental discovery, offering a direct glimpse into the fundamental forces that govern matter itself. Or perhaps we'll find hyperons. These are strange baryons, similar to protons and neutrons, but containing one or more strange quarks, in addition to up and down quarks. They are heavier than normal nucleons, and their presence could significantly soften the equation of state, making neutron stars more compressible. This could have profound implications for the maximum mass a neutron star can support. And then there's the truly speculative yet tantalizing possibility of strange matter. This isn't just matter containing strange quarks, it's a hypothetical ultra-stable form of matter where up, down and strange quarks exist in roughly equal proportions. If strange matter is more stable than ordinary nuclear matter, neutron stars could actually be strange stars, composed entirely of this exotic substance. This would be a game changer, fundamentally altering our understanding of the universe's building blocks. The point is, the inner core of a neutron star is the ultimate cosmic laboratory. It's a place where the known laws of physics are pushed to their absolute limits, and where entirely new states of matter, unlike anything we've ever encountered, might be waiting to be discovered. The grand synthesis, theory meets observation. Understanding neutron stars is a magnificent cosmic dance between theoretical predictions and observational verification. Physicists develop sophisticated models and run mind-bending simulations, trying to predict how matter behaves under these extreme conditions. They then compare their predictions to the data streaming in from NICA, from LIGO, Virgo, CAGRA, and potentially from future neutrino detectors. It's an iterative process. Observation constrains theory, theory guides new observations, and gradually, painstakingly, we refine our understanding. Every new detection of a neutron star's mass and radius, every gravitational wave chirp from a merger, every potential neutrino burst from a supernova is a piece of a giant cosmic puzzle. We are on the verge of stitching these pieces together to reveal a clearer picture of these enigmatic objects. The cosmic payoff. Why this matters. So, why does all this matter? Why dedicate so much effort, so much ingenuity to understanding these tiny, dense cosmic remnants? Because neutron stars are more than just fascinating objects. They are unparalleled laboratories for fundamental physics. They allow us to test Einstein's theory of general relativity, in the most extreme gravitational environments imaginable, where space-time is warped and stretched to its limits. Uncover the nature of strong nuclear force, the fundamental force that binds quarks together and holds atomic nuclei intact under conditions we can never replicate on Earth. Understand the origin of heavy elements, confirming their role as the universe's ultimate alchemists, forging the gold, platinum and uranium that make up our planet and ourselves. Explore the limits of matter itself, pushing our understanding of density and pressure to unimaginable extremes, potentially revealing new phases of matter that rewrite our textbooks. Decipher the dynamics of stellar evolution, helping us understand the violent deaths of massive stars and the subsequent cosmic recycling of elements that seed future generations of stars and planets. In essence, by studying neutron stars, we are not just learning about some distant exotic objects. We are learning about the very rules that govern our universe, the fundamental building blocks of reality, and our own cosmic origins. We are pushing the boundaries of human knowledge, daring to peer into the heart of darkness and find light in the most extreme places. The journey of discovery is far from over. In fact, in many ways, it's just beginning. The age of multi-messenger astronomy is here, and with every new signal, every new observation, we get closer to answering the profound questions that neutron stars pose. We are living in an extraordinary time, a time when the universe is starting to reveal its deepest secrets, one neutron star at a time, and we at Dreamy Science are thrilled to share every awe-inspiring moment of that revelation with you. The universe awaits, and its wonders are endless. We've journeyed through the astounding physics of neutron stars, from their birth in fiery supernovae to their roles as cosmic lighthouses, magnetic monsters, and alchemists of the elements. We've seen how they spin hundreds of times a second and wield magnetic fields trillions of times stronger than Earth's. We've even witnessed their cataclysmic mergers, forging gold in the heart of space. But even with all these incredible discoveries, one fundamental question continues to hum at the core of our understanding, a profound mystery that dictates everything we've discussed. What is a neutron star made of, really? And how does that matter behave under such unimaginable pressure? This, my friends, brings us to the ultimate frontier in neutron star research, the quest to pin down this equation of state for ultra-dense matter. Imagine trying to describe a substance so extreme that a single sugar cube of it weighs 1 billion tons. What happens to atoms, to neutrons, to even quarks, when they are squeezed tighter than anything we can ever replicate on Earth? That's what the equation of state seeks to answer. It's a mathematical relationship that tells us how the pressure inside a neutron star changes with its density and, to a lesser extent, its temperature. Think of it as the ultimate cosmic recipe, dictating the ingredients and their interactions within this super-compressed stellar core. Why is this so crucial? Because this single equation governs everything about a neutron star's macroscopic properties. It determines how big a neutron star can be, its maximum mass, how large it is for a given mass, its radius, and crucially, what exotic forms of matter might be lurking deep within its core. A stiff equation of state means the matter resists compression strongly, leading to larger radii and potentially higher maximum masses, with the core perhaps remaining mostly neutron-rich. A soft equation of state, on the other hand, means the matter is more compressible, resulting in smaller radii and lower maximum masses, potentially opening the door to strange new particles and phase transitions. This isn't just an academic exercise. It's about pushing the very boundaries of physics. It's about understanding how matter behaves when it's so dense that the strong nuclear force, the very glue that holds atomic nuclei together, is pushed to its absolute limits. It's about bridging the gap between the tiny quantum world of subatomic particles and the colossal gravitational realm of relativistic astrophysics. So how do we, humble inhabitants of a relatively fluffy planet, hope to solve such a profound cosmic riddle? We turn our eyes and instruments to the stars themselves, using neutron stars as the ultimate laboratories. One of our most powerful tools in this endeavour is the Neutron Star Interior Composition Explorer, NISA. Perched on the International Space Station, NISA isn't just any X-ray telescope, it's a precision timing instrument. Remember how some neutron stars, particularly pulsars, have hotspots on their surface? As the neutron star spins, these hotspots sweep across our line of sight, creating incredibly precise X-ray pulses. NISA precisely measures the arrival times of these X-ray photons. By analysing these tiny variations in brightness and their timing, scientists can actually map the surface of the neutron star and, crucially, determine its mass and radius with unprecedented accuracy. Imagine trying to measure the size of a billiard ball from hundreds of miles away, while it's spinning faster than a blender, and only catching glimpses of its surface through a flickering light. That's essentially what NISA does, but on a cosmic scale. By observing pulsars like PSR J030/0451 and PSR J0740/620, NISA has provided the most precise mass radius measurements to date, and these measurements are direct constraints on our elusive equation of state. If we find that a neutron star of a certain mass has a surprisingly small radius, it suggests a softer equation of state, hinting at highly compressible matter. If it's larger, it points to a stiffer one. Each new measurement is like adding a crucial piece to a gigantic universe-sized puzzle, slowly revealing the true nature of matter at its densest. But NISA isn't working alone in this cosmic detective story. We also have our ears to the ground, or rather, to the fabric of space-time itself, listening for the whispers of gravitational waves. Remember our discussion of binary neutron star mergers, like GW17081 SIN. Those cataclysmic collisions aren't just spectacular fireworks, they're also profound probes of the equation of state. As two neutron stars spiral closer and closer, their immense gravitational fields begin to distort each other, stretching and pulling them into elongated shapes. This phenomenon is called tidal deformability. Think of it like a cosmic tug-of-war where the stars are pulled by their mutual gravity. How much they deform, how squishy or stiff they are under this extreme tidal force directly imprints itself onto the gravitational waves they emit. A stiffer neutron star will resist deformation more, meaning it's harder to stretch and squish. This will affect the precise pattern of gravitational waves in the final moments before the merger, allowing the stars to get closer before they finally collide. A softer neutron star, being more pliable, will deform more easily, affecting the gravitational wave signal differently and causing the stars to merge a little earlier. By meticulously analysing the gravitational wave signals detected by observatories like LIGO and Virgo, scientists can deduce the tidal deformability of the merging neutron stars. And just like NISA's mass radius measurements, these tidal deformability constraints provide invaluable insights into the equation of state. The beauty of this is the complementarity. NISA gives us precise snapshots of individual, isolated neutron stars. Gravitational wave astronomy gives us dynamic information about neutron stars under extreme stress during a merger. Both approaches, using different cosmic messengers, are converging on the same fundamental question. They act as independent cross-checks, building a more robust and accurate picture of the universe's densest objects. And what is the ultimate prize in this quest for the equation of state? It's the potential discovery of our exotic matter in the neutron star core. This is the great unresolved mystery we mentioned earlier. If the equation of state turns out to be soft enough, it implies that at the incredible densities found in the inner core, neutrons themselves might break down. We could be looking at a phase transition, much like water turning into ice, but infinitely more profound. Instead of a sea of neutrons, we might find a soup of hyperons, baryons containing strange quarks, or even a quark-gluon plasma, where the quarks and gluons that normally reside inside protons and neutrons are no longer confined, but instead roam freely. Imagine that. If we confirm the existence of quark matter in neutron star cores, it would revolutionize our understanding of fundamental particles and forces. It would mean that the strong nuclear force which binds quarks within hadrons can effectively be overcome by gravitational pressure, leading to entirely new states of matter. It would be direct evidence of physics beyond the standard model of nuclear matter, pushing our theories to their absolute limits and potentially revealing new fundamental particles or interactions. Conversely, if the equation of state proves to be stiff even at the highest densities, it would suggest that the neutron-rich matter remains remarkably stable, perhaps hinting at unexpected properties of the nuclear force itself. Either way, the answer will be groundbreaking. The journey doesn't end here, of course. Future gravitational wave detectors, like the proposed Cosmic Explorer and Einstein telescope, will offer even greater sensitivity and precision, allowing us to detect more mergers and constrain the equation of state with even greater accuracy. And the nascent field of neutrino astronomy holds the promise of peering directly into the heart of supernovae and neutron star mergers, potentially revealing the dynamics of these extreme environments in real time. This research, at its heart, is a grand collaborative effort, drawing together nuclear physicists, astrophysicists, general relativists, and observational astronomers from around the globe. It's about using the most extreme objects in the universe to test the most fundamental laws of physics. Neutron stars are not just fascinating cosmic curiosities, they are cosmic laboratories, enabling us to explore conditions that are utterly unattainable anywhere else. So as we continue to gather more data, to refine our models and to push the boundaries of our understanding, we are slowly, painstakingly piecing together the ultimate secret of the neutron star. What is it truly made of? What wonders lie hidden beneath its impossibly dense crust? The answer to the equation of state for ultra-dense matter is not just an astrophysical detail. It is a profound revelation about the very nature of reality, about the resilience and transformation of matter itself under the most extreme conditions the universe can conjure. We are living in an incredible era of discovery, where the universe is literally whispering its deepest secrets to us. And with every new piece of information, with every new measurement, we get closer to understanding the heart of these enigmatic, awe-inspiring objects. The quest continues, and with it, our collective wonder only grows. All right, dreamers. We've journeyed deep into the heart of neutron stars, peeling back layers of their incredible density, their bewildering magnetism, and their explosive cosmic dance. We've seen how these stellar remnants push the very fabric of space-time to its absolute limit, challenging our understanding of the universe. But as we hinted, there's one monumental mystery that still largely eludes us, a puzzle piece that could unlock the ultimate secrets of these cosmic titans. The equation of state for ultra-dense matter. Think of it like this. If a neutron star is a cosmic safe, the equation of state is the combination. Crack that, and we open the safe to reveal not just what's inside, but how. It behaves under the most unimaginable conditions. It's the Holy Grail, the Rosetta Stone for understanding matter itself at its most extreme. So how do we, the curious explorers of dreamy science, even begin to decipher such a cosmic code? We can't simply slice open a neutron star and peer inside, can we? No, our approach is far more ingenious, far more astronomical. We observe, we measure, we listen to the universe's whispers and roars. One of our most invaluable tools in this cosmic detective work is a mission we've talked about before, NICER. The Neutron Star Interior Composition Explorer. Remember how we said it's perched on the International Space Station acting like a super-sensitive X-ray eye? Well, NICER's primary mission is precisely this, to measure the mass and radius of neutron stars with unprecedented accuracy. Why are mass and radius so critical? Imagine you have a balloon. If you know how much air is in it, mass, and how big it is, radius, you can start to infer things about the material it's made from. Is it thin and stretchy, or thick and rigid? For a neutron star, it's vastly more complex, but the principle holds. Different equations of state, different theories about how matter behaves under such crushing pressure, predict different relationships between a neutron star's mass and its radius. If the matter in the core is stiff, meaning it resists compression strongly, then for a given mass, the neutron star will be larger. If the matter is soft, meaning it's more compressible, then for the same mass, the star will be smaller, denser. It's a cosmic game of squeezability, and NICER is giving us the vital clues to play along. By precisely measuring the X-rays emitted from the hotspots on a spinning neutron star, NICER can map its surface and infer its size and heft. It's like trying to weigh and measure a rapidly spinning, impossibly tiny, incredibly heavy ball from millions of miles away, using only the light it emits. Mind-bending, right? But NICER is just one piece of the puzzle. The universe, in its infinite generosity, has provided us with an even more spectacular and direct window into the heart of neutron stars. Gravitational waves. Cast your mind back to those cataclysmic neutron star mergers we discussed, events like GW 170817. When two neutron stars spiral inward, locked in a death embrace, their immense gravitational fields distort and ripple through space-time. These ripples, these gravitational waves, carry information about the stars themselves, right up until the moment they collide. And one of the most profound pieces of information they carry is about something called tidal deformability. What is tidal deformability? Imagine you have a perfectly rigid steel ball. If you bring another massive object close to it, the steel ball won't change shape much. Now, imagine a squishy rubber ball. Bring that same massive object close, and the rubber ball will visibly distort, stretching and squeezing due to the gravitational pull. That's tidal deformability in action. How much an object squishes or deforms under the gravitational influence of another nearby body. For neutron stars on the brink of collision, the gravitational tides exerted by each star on the other are immense. How much they deform, how much they give under this incredible stress, tells us directly about the stiffness or softness of the matter deep within them. If they deform easily, their internal matter is soft. If they resist deformation, it's stiff. And guess what determines that stiffness or softness? You got it. The equation of state. The gravitational wave signal from GW 170817, that incredible cosmic symphony, didn't just confirm the existence of neutron star mergers. It also provided the first direct constraints on the tidal deformability of neutron stars. This single event, a cosmic collision of epic proportions, gave us a glimpse into the internal physics of these objects in a way no other observation ever could. It was like finally getting a direct measurement of the squishiness of a sugar cube weighing 1 billion tons. So we have NICER giving us mass and radius, gravitational wave observatories like LIGO and Virgo giving us tidal deformability. Together, these measurements act like cosmic calipers, squeezing down the possibilities for the equation of state. They help us rule out certain theoretical models and refine others. It's a beautiful example of multi-messenger astronomy in action, where different types of cosmic signals, X-rays, gravitational waves, gamma rays, radio waves, all converge to paint a more complete picture. Now let's get to the juicy part. What are these equations of state telling us might be lurking inside? What exotic forms of matter could be responsible for the observed squishiness or stiffness? At the simpler end of the spectrum, some models suggest that a neutron star's core might largely remain a superdense soup of neutrons, perhaps with a small percentage of protons and electrons, all interacting via the strong nuclear force. This is the neutron soup model, where the degeneracy pressure of the neutrons is the dominant force pushing back against gravity. But what if the pressure gets so high, so utterly unfathomable, that even neutrons themselves start to break down? This is where things get truly mind-bending, where the realm of nuclear physics meets the cosmic extreme. One fascinating possibility is the formation of hyperons. Remember how neutrons and protons are made of up and down quarks? Well, there are other types of quarks, like strange quarks. Under the immense pressure in a neutron star's core, it might become energetically favourable for some of the up and down quarks to transform into strange quarks, leading to the formation of particles called hyperons. If hyperons exist in the core, they would introduce new ways for matter to compress, potentially making the equation of state softer than if it were just pure neutronium. This means the star might be smaller for a given mass. It's like adding new, more compressible ingredients to our cosmic pressure cooker. And then there's the ultimate, most exotic possibility: quark-gluon plasma. Imagine squeezing matter so hard the individual neutrons and protons themselves melt away. Their constituent quarks and gluons, the fundamental particles that make them up and the force carriers that bind them, are no longer confined within individual particles. Instead, they form a free-flowing soup or plasma. This state of matter is theorized to have existed for a fleeting moment after the Big Bang, and we can briefly create tiny pockets of it in particle accelerators here on Earth. But in the core of a neutron star, it could exist stably, eternally, under the most extreme conditions. If a quark-gluon plasma exists, it would represent a fundamental phase transition in matter, a complete reorganization of its very building blocks. Depending on the exact properties of this plasma, it could make the core either softer or, surprisingly, even stiffer under certain conditions, influencing the star's overall mass-radius relationship and tidal deformability in complex ways. And for the truly speculative, some theories even propose that a tiny amount of dark matter could accumulate in the cores of neutron stars. If dark matter particles interact with baryonic matter even weakly, their presence could subtly alter the equation of state, adding another layer of mystery to the neutron star's internal structure. It's a tantalizing what-if that reminds us how much we still don't know about the universe's invisible components. So why does any of this matter? Beyond satisfying our boundless curiosity, why dedicate so much effort to deciphering the equation of state of these distant extreme objects? Because, my friends, understanding neutron stars is not just about understanding neutron stars, it's about understanding the fundamental physics itself. These objects are living laboratories, pushing the boundaries of what we know about the universe. They are the ultimate stress test for Einstein's theory of general relativity. Their immense gravity warps space-time to an extent that is simply unimaginable, allowing us to probe the theory in regimes far beyond what we can achieve even in our most powerful laboratories. Any deviation from Einstein's predictions in such extreme environments would be revolutionary, potentially pointing towards new theories of gravity. They also provide an unparalleled window into the strong nuclear force, the fundamental interaction that holds atomic nuclei together. We study nuclear physics on Earth, smashing particles together to understand how quarks and gluons interact. But in a neutron star, we have a macroscopic object miles across, where these forces are playing out on a grand scale, under pressures and densities that are utterly unattainable in any terrestrial experiment. It's like having a cosmic particle accelerator that's been running for billions of years, giving us a unique perspective on the most powerful force in the universe. And let's not forget their role in the origin of elements. Remember those kilonovae, those brilliant explosions from merging neutron stars? We learned that these events are the cosmic crucibles where heavy elements like gold, platinum, and uranium are forged. The details of the equation of state influence the dynamics of these mergers, affecting how much material is ejected and what elements are produced. By understanding the neutron star's interior, we better understand the cosmic alchemy that gave rise to the very building blocks of our jewelry, our technology, and even parts of our own bodies. Ultimately, the quest for the equation of state is a quest to understand the very nature of matter itself. What happens when you squeeze matter harder than anything else in the observable universe? Does it simply become a super dense fluid of neutrons? Or does it undergo a profound transformation into something entirely new, something exotic and mind-bending? It challenges our deepest assumptions about the stability and composition of matter, pushing the limits of our knowledge. The journey to crack this cosmic code is far from over. Future generations of gravitational wave observatories like the planned Cosmic Explorer and Einstein telescope will provide even more precise data on neutron star mergers, refining our measurements of tidal deformability and further constraining the equation of state. Next-generation X-ray telescopes will continue to improve our mass and radius measurements, and perhaps even detect subtle signatures of phase transitions within the star. And here on Earth, our particle accelerators and nuclear physics experiments will continue to probe the strong force from the ground up, providing complementary insights that help us interpret the astronomical observations. The universe is constantly revealing its secrets piece by astonishing piece. And with every new discovery about neutron stars, these densest objects in the universe, we don't just learn about distant cosmic phenomena. We learn more about the fundamental laws that govern everything, from the smallest subatomic particle to the grandest galaxy, and ultimately about our own place in this wondrous, astonishing cosmos. So as we bring this chapter to a close, I want you to carry with you this sense of profound wonder. The neutron star, a tiny, super-dense remnant, is a key to unlocking some of the universe's biggest mysteries. It's a testament to the power of scientific inquiry, to our collective human drive to look up at the stars and ask, how and why? What do you think lies at the heart of a neutron star? A simple neutron soup or something far more exotic? Let me know your thoughts in the comments below. And if you've enjoyed this mind-bending journey, please give us a like and subscribe to Dreamy Science for more cosmic adventures. We're just getting started.